Yeah. So I'm going to talk about GroundBIRD, which is a CMB experiment here in Tenerife. So on behalf of the GroundBIRD collaboration, if I go to the next slide, there we go, which is quite a big collaboration, mostly based in Japan, Riken, Kyoto, and various other places. Also has links with Korea University and KASI in both in Korea, S1 in the Netherlands, and here at the IAC where the telescope is based. So the overall goal for GroundBIRD is the largest angular scales on the sky to make very high sensitivity measurements of those between L of 6 to about 300. So the main goal obviously is B modes, so particularly the tensor scale ratio R down to sigma R levels of about 0.01. We also want to look at E modes, the optical depth to reionization from those, which are dominating at these larger angular scales. So we think we can get uncertainties from that down to about 0.03, or better if you combine with other experiments. We'll also look, of course, at the polarized thermal dust emission, both the amplitude and also the spectral index, because we're low frequency than the Planck 353 gigahertz, so you get spectral information out from that. And a really important thing is this is a northern hemisphere observation. So it's very complementary to south observations. You're looking at a completely different part of the sky. So different modes apart from the very low multipole. This is particularly important if you want to understand things for LightBIRD, because obviously that's a full sky satellite mission. So it helps if you have experiments both in the north and in the south to be able to get full sky information for LightBIRD. So the specifications, so we've got a focal plane which is cooled down to less than 0.3 Kelvin. We have various coolers to do that. The main one is a sorption cooler at the very lowest temperatures, and the PTC to get down to 40K. So you can sort of see this in the figure here. So we've got various layers going in. The mirror is actually in the center. So we've got a 40 centimeter mirror cross-to-grown setup in the cryostat. And that's cooled down to 4 Kelvin. So that helps with the thermal noise from the mirror itself. And then we have a large focal plane, which is, as I said, cooled down to about less than 0.3 Kelvin. And that has kids detectors in it, which are at 145 gigahertz, 150, I can interchange them, and 220 gigahertz. And the aim is to have 7 arrays, each of which have 23 pixels. So that gives you about 160 pixels in total. And that's split between mostly 150 gigahertz and one at 220 gigahertz for thermal dust emission. So the resolution on the sky this gives you is about 0.5 degree to 0.3 of a degree, depending on the frequency. So this is the telescope with the standard human for scale. So it's quite a big, well, huge cryostat, a couple of tons, I think, in total. And this, I'll say in a second, rapidly rotates to scan the sky. So the really important thing here is having stability, so you can actually recover the large angular scales, which requires minimizing all of the 1/f emission you get from detectors, from the atmosphere, from anywhere else. So the way GroundBIRD approaches this, which is pretty unique, is a continuous, very fast spin. So it has a rotary joint at the bottom, so it can continuously spin. You don't have to slow it down or anything. And it can go at, sorry, apologies, there's a plane flying over, so apologies if you hear background noise. It spins at 20 rotations per minute, so that's once every 3 seconds at a fixed elevation, which can be between 60 and 90 degrees. So that immediately cuts out any on timescales which are larger than 3 seconds, because that's a full rotation. And of course, you can do better than that if you then have destriping as well. There's a lot of magnetic shielding around the cryostat because MKIDs can be affected by magnetic fields, particularly that of the Earth. And there's very stable cryogenic temperatures during operations. So there's a lot of mass inside the cryostat. It actually takes a couple of weeks to cool down, about the same amount of time to warm up afterwards. So it's very, very stable. The exception for that being the sorption cooler has to be regenerated every day. So it lasts for about 20, 21 hours at cryogenic temperatures. Then you need to warm it up to about 4 Kelvin, regenerate it, and then cool it back down afterwards. And that cycle takes about 3 hours, which we mostly do actually when the sun is above our elevation range. So we can't observe it anyway then because the sun will contaminate. So it doesn't affect the integration time we can get too badly. There's also a lot of other procedures. So for example, the humidity in the dome is very well controlled. And the dome is inside a ground shield. So that means it's sheltered from the weather, from ground radiation, from anything else going on around it at the site. So hopefully should be very stable and very protected. The observations are taking place at Tedy Observatory in the CMB area. So this has actually been in use since 1984 for CMB observations, starting with a Tenerife experiment. Ricardo is actually going to talk more about this, everything else at the site later, so I'll skip most of this. Just to say, it's next to Cahote, and this is a former very small array enclosure. VSA was actually in the top one, and source subtractors in the bottom two, but GroundBIRD is now installed in the southern area from there. This is all at an elevation of about 2,400 meters, which means we've got a medium perceptible water vapor of about 3.8 millimeters. It can get very low up there, down to less than a millimeter. This is both because of the height, also because of the Azores anticyclone structure, which means that the cloud level is actually below the observatory most of the time. It does occasionally come through the observatory, but most of the time it's below, and it's very stable, very good atmosphere at the site. Even better than you get at higher altitude sites elsewhere, just because you've got the structure around the area. This is at 28.3 degrees north, and we're scanning at about 60 degrees elevation at best. So we get declinations on the sky between about -2 and +58 degrees on the sky. And the focal plane has an instantaneous view of about 10-15 degrees circular. So that means with Earth's rotation, we end up mapping out about 50% of the sky. So most of the north, and we're going into the south a little. The focal plane is this setup here. So this is all cooled down to 250, well, yeah, this is cooled down to 250 millikelvin. You've got an outer one, which is 350 millikelvin, and then the very outer layer is down at 4 Kelvin. And you can see the MKIDs in these arrays here. So we're using, yeah, so before 150 gigahertz and 220, 220 is mostly for the dust. We're using MKIDs that look like this. So you have a small antenna at the top, and then it feeds into a feed line, and it inducts a signal into that feed line. And by putting a lenslet on top of that, you increase the antenna area, basically. So these are very simple construction, have very broad bandwidths, and you can hopefully have quite a few of them in here. It's limited by the size of the lenslets, basically. So we started doing initial observations with just 3 pixels, 150 gigahertz, and a 14 pixel array at 350 gigahertz, which we actually filtered down to about 220. We got first light with that back in 2019. We've since upgraded the detector array, so we now have 2 23 pixel arrays. One of these is from Riken in Japan, and one is from Esron, and both are under test at the moment. They both have currently 2 polarization directions, so we can recover some polarization with this. And the plan is to build a full set of 7 of these, probably from Esron, with 4 polarization directions, so we can fully recover Q and U. That's done separately for each KID, so each KID has a particular polarization alignment, and you combine multiple KIDs together to get the polarization information. And yeah, the aim is to fully populate this sometime next year. And it'll look like these silver holders very close together. This big gold one is a temporary one. I don't have time. Okay. The readout system is again quite simple. So you need to inject input tones into the cryostat at the resonant frequencies that you've measured for the KIDs. And then you read out the result of that tone after the resonances and measure the change in the amplitude and phase. This is done at frequencies around 5 gigahertz. You have one field programmable gate array per wafer, and that reads out all pixels from that wafer, so 23 in this case. And that has a bandwidth of about 250 megahertz at the moment, so you can separate them out quite nicely in that. And we're sampling, well, we're aiming to fully sample the beam, even though we've got a very high rotation speed. So 20 rotations per minute. We want kind of at least 5 samples per beam size, which is about half a degree compared to 360 all the way around. So we need about 1,000 samples a second, which is quite fast. That can be a problem for some types of detectors. For example, some bolometers have a long time constant afterwards, but MKIDs have a very fast response, so it works out really well with them. So you don't get any lag or anything like that when you're reading it out. And this is just a picture of one of the FPGAs with the ADC and some of the RF side of it, and a quick diagram on the other side. So basically, it's a circuit. You inject some signals with a digital to analog converter, you send them into the cryostat, resonates against it, and then you read out the resulting one with your ADC and compare them. We also have a lot of other monitoring going on at the site. So we have local weather information from multiple stations across the observatory, so Stellar and Song and various other telescopes at the site. We measure the atmospheric precipitable water vapor through GPS measurements, which we get from AEMET, which is the Spanish meteorological organization. You can actually see them in the background from the observatory. It's the weather station they've got right next to the observatory. We're monitoring clouds through an infrared camera, which is developed by the Korea University, and you can see that in this picture here. So this basically has 4 cameras inside it, which could give you most of the sky above you, at least the range we need for GroundBIRD. We also have, within the dome structure and areas, we have local rain, humidity, temperature, pressure sensors, so we can record all that. And by the way, the pressure sensors did detect the eruption of the volcano on the other side of the planet, and quite a few meteorological stations were seeing last year. We also monitor aircraft through an ADS-B receiver, and we've got webcams, thermometers, and everything else to keep an eye on everything, and lots of Raspberry Pis powering all of these things. So we've done initial calibration measurements, moving on to the survey now. Just to show you, this is what the moon looks like from GroundBIRD. With this is a 26 pixel array. I said 23 before because only 23 of them normally have lenslets. We have the other ones just have the antennas, so we don't normally use them, but you can see all 26 in this plot. This is because the moon is really bright and easy to observe at these frequencies. So we've been observing it when it's been either rising or setting at fixed elevations, normally about 70 degrees. We've also done 80 and a few others. And this happens basically for the period of a week every month or so. So far, we've mostly been using the S1 145 gigahertz detector for this. We've also got data from the RICAN and from the other S1 350 gigahertz detector. And in this case, we only had 4 lenses installed, so 22 of these are only with antennas, but you can still see you're getting the high signal to noise from the moon. But you can see some of these have a lot better defined beam, which is the ones which have the lenslets in place. And also we've been doing tests like telescope pointing using the moon observations, which is all looking good. So this is what Yoshinori put together, just showing the difference between the peak of the centers of the moon and the positions they expect it to be on the sky in elevation and azimuth. And this is down at the 1 arc-minute resolution. So that's very small compared to our half a degree beam. So that's all looking good. Something we've been doing recently, which has been quite fun, is calibration with wire observations. So the idea here is you put a wire across the top of a telescope and you rotate the telescope underneath it. This is a concept from Quiet, so there's a reference down there if you want to see the background behind it. But the basic idea is you get a peak whenever you're observing the wire, which depends on the polarization angle of the detectors compared to the angle of the wire. So you can use this to calibrate polarization. And this was just a quick measurement we did where you can clearly see you've got, this is scanning 360 degrees and all the different channels with an offset. And you can see clearly there's peaks in pretty much all of these at the right positions. It's very high-tech setup using a rake each side of the dome area just to hold that wire above the dome because that can be a bit tricky. There was a paper that came out in last year, in 2021, which was by Qiming Li, and that was talking about the forecast for the cosmological parameters that we will get. So that was where the numbers I gave earlier came from. There was actually a talk about this by Qiming last year at Cosmoglobe, so see that talk for all the details, or the paper, of course. But the basic numbers are, we're forecasting we get a sensitivity of about 110 micro-K arc minute, 150 gigahertz. It goes up to about 780 microkelvin at 220 because we've got fewer detectors. But the main one for CMB is 150 gigahertz. And that gives an uncertainty on tau of about 0.03 just with GroundBIRD on its own. An important thing here, though, is foregrounds. So you need to understand them pretty well to make sure you're actually observing the E-modes from CMB. So if you include Cahote data from the same site with this, then you get down to about 0.01. So that was interesting forecast. And you can see the noise levels as well. So this is without Cahote and with Cahote, and the noise level in your recovered EMAP is a lot better when you can accurately remove the foregrounds from that. So the current status of the telescope is basically we're starting fully remote observations now. So we can fully automatically open and close the domes, start and stop rotation, everything like that. There's been quite a lot of work to do, as well as to make sure that the whole site is secure, so no one can actually accidentally wander into the site when the telescope is operating anymore. We're currently observing at 70 degrees, which is the lowest we can go. So we actually need to do a tweak of the helium pipes to go down to 60 degrees, which we can do in principle. So it should be a relatively minor change at some point. The limitation there is you can't tilt the pulse tube coolers or the sorption coolers too much. So you can do to about 30 degrees, but not much more than that. So stuck to about 60 degrees as a maximum elevation. And we are actually warming up right now because we've got a small issue with the thermal links, which degrade when you've warmed up and cooled down too many times. Basically, you have the Kevlar links that start to give way, and you just need to tighten them. So we're going to do that in a few weeks, and then on to science observations. So just to give you an idea of the timeline, so in 2018, we had the dome installed at the site. 2019, the instrument was installed, and we got first light in September that year. The picture on the right is the insides of the cryostat, which we lift out in one go to work on this. And that top plate is the top plate of the cryostat. So normally this will all be inside the cryostat. But yeah, for GroundBIRD, kind of flying a bit, but only with the plane, so it's okay. So we had the COVID slowdown in 2020, 2021, meant no one from Japan could come work on a telescope or anything like that. So that affected us quite a lot in those years. But in 2021, we were able to resume initial observations, and we were doing the initial calibration with the moon and the wire, and some initial long run measurements as well. This year, we've had 2 times 23 pixel wafers installed, and we've set up everything for remote observations. So we no longer have to spend nights at the observatory trying to observe the moon, which is quite good. We can do everything from the comfort of our home now. So the idea is next month, we basically start with science observations with the 2 wafers and get integrated, so we get a lot of data with those. And then simultaneously, the next set of wafers will be constructed a test run, and in maybe March next year, we'll be able to upgrade to the full set of 7 wafers and do the full science observations then. We'll probably do a continuous survey then until something like 2025. There's also ongoing discussions about whether it's worth changing frequency, so adding in 90 gigahertz as well as one of the main science channels, just so we can understand the foregrounds more and we integrate for longer with the instrument at different frequencies as well. So that's the conclusions. So basically, GroundBIRD is fully installed and prepared for remote observations, and we're starting routine science observations shortly. The aim is about 110 microkelvin arc minutes in the Northern Hemisphere. Again, is very complementary to Southern Hemisphere observations. And just with this data, we estimate we'll constrain it out to about 0.03 or to about 0.01. And this is just an overview of the site. So you can see GroundBIRD just in the dome here next to Cahote observing with some optical foregrounds. And if I've got a couple more minutes, I've got one bonus slide, if that's okay.
Fine by me.
Okay, and then go on to questions. So just something I've been worrying about a lot for the last few years is there's now a lot of satellites being launched in their thousands as part of Starlink and other constellations. And these are actually starting to transmit at CMB frequencies. So I kind of just want to give a general warning for others observing these frequencies for that. So mostly they're at KU band, so they'll be moving up to KA band. They have a lot of V band planned, and you get all the octaves, so you can see them even at very high frequencies. So there's increasing amounts of geostationary satellites up there because KU band is now full. So people are moving to KA band to be able to get transmission slots, basically. And this can become an increasing issue for CMB. It can be really complex to remove because of main beam and side lobes. Particularly the side lobes can be complicated. So just mention there's going to be a discussion of this at the CMB S4 meeting next week. And there was also a discussion at Dark and Quiet Skies conference last year. And it's just some of the frequencies that we know that are going to be transmitting at, which will affect some instruments here in Tenerife. And a fun, by the way, I found out WMAP is actually commonly seen by optical telescopes as a source of interference there. So it's one of the brighter satellites apparently in optical. So it goes both ways. But yeah, that's everything I've got. So thanks for listening. Any questions?